Hi, everyone. My name is Richard Zhou. I'm on the PyTorch team at Meta, and today I'll be talking about blazing fast GenAI Inference with Torch.compile. So we'll do a quick introduction to Torch.compile first. So you guys have probably heard it talked about it a lot at this conference, but Torch.compile is a just-in-time compiler. It captures straight-line graphs that can be optimized. So you can apply Torch.compile to a function. It'll do a front-end capture of the function to produce a graph. And then this graph is passed to our backend inductor, which will produce efficient output code in the form of fused Trident kernels and potentially other things as well. So why use Torch.compile? The value proposition of Torch.compile is that it gives you fast baseline performance to save development time, like from tuning model performance. So I've got a flowchart here. Question is, do you want to spend a long time like hand tuning your kernels? If the answer is yes, like there's been a bunch of cases in the past where people have just handwritten a kernel and Torch.compile is still faster. Okay, and some examples of performance. So on the bottom right, this was a recent X post, Twitter post in the last couple of months where they enabled Torch.compile on the Gemma 3 model in HuggingFace transformers and saw something like a 60% speed up. At the top right, the PyTorch compiler team keeps a benchmark of models and just a list of speedups. In this table, you can see something ranging from like 1.02x to up to like, I think it's like 2.7x, which is a lot. And on the bottom right, we'll talk a bit more, but vLLM uses Torch.compile by default, and this gives like, we've seen performance numbers like ranging from like 1.05x to 1.9x. So in this talk, like I want to walk through how like Torch.compile generates fast kernels, lets you reduce CPU overheads, and also lets you sort of automate custom optimizations. We'll start small from a simple like layer norm kernel use case, build up to using HuggingFace, Torch.compile and HuggingFace diffusers, and then talk about a very involved use case for text generation in vLLM. Before we begin, I want to say that Torch.compile is a learnable skill. Like you can use Torch.compile out of the box, maybe without much knowledge. It may or may not make your code faster. To really like use Torch.compile well, you have to learn to manage your compilation process. In particular, you'll need to learn about things like graph breaks, how to manage your compilation time, recompilations, dynamic shapes, and custom operators. And we'll see examples of these 5 things in the slides today. So first case study is a layer norm kernel. We're going to talk through like how to reduce graph breaks, full graph compilation, and recompilations. I like this example because it's just some really simple code. So layer norm kernel, you're got some input tensors. It's going to return an output tensor. And if you just apply Torch.compile to this, like the regular call to layer norm is without Torch.compile in this example is 1.4 milliseconds on my machine. If you apply Torch.compile to this, to the function, it goes down to 0.5 milliseconds. So that's a lot of speed up already. What else can you do? The first thing is I kind of snuck this print statement into the middle of the layer norm function. Torch.compile's front-end Dynamo does this thing where it will break the graph. It'll create a graph break on anything it doesn't support. And so like in this case, like Torch.compile decides to graph break on the print function. So why doesn't Dynamo support print functions? The idea is that it's just very conservative. Like maybe Dynamo can move your print function to the end so that it can have like one big graph that it compiles. Dynamo decides that, hey, okay, maybe you really want your print here, so we're just going to graph break. And so graph breaking here means that there's actually 2 graphs being captured, one at the top, one at the bottom. And these 2 graphs get sent to the backend separately for compilation. So this is, on the right is a like page from TLParse. TLParse is a tool where you can actually look at what is happening with Torch.compile. So in TLParse, like very top, the font might be a bit small, but it's a link to the graph break. And the graphic, it tells you exactly what it is. It's a print statement in your code. if you click through the compilations, of which there are 2, you can actually look at the inductor output code. And for each of these graphs, inductor generates 1 fused trident kernel for each of those 2 graphs. And so to make this thing faster, like this entire thing can be fused into 1 single kernel. And you just have to remove the graph break. And sorry, before I go to removing the print statement, another way to figure out like where your graph breaks are is you can call Torch.compile with full graph equals true. And it'll straight up error, like if it sees a graph break, with the same message that the TL parse would have shown you. So removing the print statement gets you down to 0.25 milliseconds, which is great. Everything's 1 fused kernel. You're pretty happy. Except for recompilations. So one interesting thing to note about Torch.compile is that it really specializes on your inputs. What this means is that like it will look at your input shapes and it'll be like, okay, I'm going to compile a kernel or multiple kernels like for these exact input shapes. And this is not desirable sometimes, especially in like a GenAI use case where like for like LLM text generation, you have like varying batch sizes, you have varying number of tokens. For image like generation, maybe you have different image sizes. So in this layer norm example, like maybe we varied the dimension in the first dimension. And so like when the shape changes, Torch.compile will recompile. Recompiles are expensive. Maybe you don't want that. And the answer to that is to just use dynamic shapes. If you know what dimension you're going to vary, you can tell Torch.compile using this Mark Dynamic API. You can say, hey, Torch.compile, I'm going to change the first dimension. Please treat it as dynamic. And what Torch.compile will do is, like Dynamo, like the front end will just treat a static graph, where the shape of the like first input is an input to the graph. If you don't know what dimensions are dynamic, or you just want something to work really fast, use dynamic equals true. It'll try to assume that all dimensions are dynamic. This comes at the downside of like increased compilation time, and Torch.compile will not be able to generate as good code if everything is dynamic. So that's layer norm. We can move on to something a bit more complicated, which is HuggingFace diffusers. So diffusers is a library for generating images, video, and audio. We're going to talk through like how to actually apply Torch.compile in diffusers. We're going to talk about how to improve compile times, and then we'll also talk a bit more about dynamic shapes. So when you're like trying to enable Torch.compile on something, like the first thing you usually ask yourself is where you should actually apply Torch.compile. Because of things like graph breaks and just like code that is unsuitable for Torch.compile being around, you want to like focus your effort on something that would have the most value. And like depending on the type of model you have, like you will want to apply Torch.compile on something different. For something like an image diffusion pipeline, like these things are not like one model, they're like multiple models stitched together. So let's say you specify some text, like a cat holding a sign that says hello world. You want to generate an image. And what ends up happening is like you have this text, you send it through a text decoder, which encodes into some embeddings. You've passed embeddings and a new latent tensor into a denoiser, which will progressively denoise the image. Denoise the latents. And then you pass the final latence tensor into an image decoder, where it'll take the latents and produce an RGB image. And in the diffusion pipeline, the diffusion transformer, the denoiser, takes actually the most amount of time. So that's the place where diffusers recommends using Torch.compile. So HuggingFace diffusers exposes the diffusion transformer as this like pipe.transformer object in your pipeline. And you can just call compile on that with full graph true. And doing this like gives you some level of speedups, with one unfortunate downside. The compilation time is actually really high compared to like the amount of time it takes to generate one single image. And so there are ways you can reduce your compilation time depending on how your model looks. So I'll talk about one technique. We call it regional compilation. It's basically compile repeated blocks separately. Like let's imagine you have a single model. It has the same like block, like repeated over and over again, modulo the parameters maybe being different. Instead of compiling all of these blocks together into one like graph, you should compile the blocks separately. And this lets us compile every block once. So let's say you have n blocks, you compile the block, like the first block once, and then reuse it n minus 1 times. And to just show how that works, let's say you have Torch.compile on a model. T0, T1, T2 are literally the same block, just different parameters. Instead of compiling the whole forward function, just compile the modules separately. And the first time you do a compile, it'll compile the kernels. The next couple of times you do it, it'll just cache it on the structure of the graph, and it'll just reuse the kernels. And so diffusers offers an option to do this. It's called compile repeated blocks. This is not a built-in PyTorch API. They just put this API into their NN modules. And it just does just that. It compiles repeated blocks. And from this, you can shave down the compile time a lot, which is really cool. One last thing on dynamic shapes. If you're the prompts that you pass, let's say you're doing inference on multiple images, on multiple text strings to produce multiple images. Like if your prompts vary in size, or if the images you're generating have different sizes, the different shapes will lead to recompilations because Torch.compile specializes on it. You can use dynamic Google string to avoid those. Okay, we're ready to go to our more complicated use case, vLLM. So vLLM is a text generation library. It's a LLM inference serving engine, which means you can start up a server, pass it some text. You can ask it what the capital of France is, and hopefully it'll tell you Paris. vLLM leverages Torch.compile by default. It uses Torch.compile for around 95% of its text generation models. We see some significant performance speedups with Torch.compile on vLLM. This is from an older benchmark with some older models, but on these the set of models from Llama, Gemma 3, and Quen, we've seen things like 1.05x speedups, 1.9x speedups using Torch.compile versus not using it. And so why does vLLM use compile? vLLM supports a pretty wide range of models, and there's a bunch of optimizations you can do to them, but it'd be nice to not optimize all of them by hand. That being said, we do want to optimize some of these models by hand, and also the stock Torch, and so that's why we use Torch.compile. Unfortunately, stock Torch.compile is insufficient for vLLM's performance requirements. That didn't stop vLLM from using Torch.compile though. And so what ended up happening was vLLM created a custom, what we call a custom compiler that's leveraging Torch.compile components to build the compiler of their dreams to optimize their code. And so I'll talk through how this integration works. We'll talk about custom kernels, piecewise CUDAGraphs, custom fusion passes, how vLLM uses this integration to give really tight control over compilation time and recompilations, and also multiple graphs for the same model. Okay, so this is an example of what happens when you compile a model in vLLM. We'll go through these steps one at a time. The first step is straight up graph capture. You've got a model, you have some example inputs. We use Torch.compile's front-end Dynamo to actually capture one single graph, one single full graph that is dynamic on the input batch size. vLLM controls the model source code for all of its models, except for the ones that use transformers backend, but that's a different story. And so all these models are handwritten to have no graph breaks and to work with dynamic shapes. A side note on custom kernels. Torch.compile generates efficient kernels for RMS storm and rope, but a lot of the vLLM operations Matmul, gems, MOEs require specialized hand-tuned kernels. Torch.compile is not able to generate good kernels for those quite yet. And so a lot of custom operations / custom kernels, if they're written in C++ and you're just calling them from Python, Dynamo does not really know what to do with it. Dynamo doesn't know if you have a side effect in them, if it's not side effectable, what the return tensor looks like. To avoid graph breaks, on custom kernels, you're supposed to wrap them in a custom operator. And that's what vLLM does. At the bottom left, it's an example of what the full graph actually looks like. vLLM hides all of their attention operations behind this unified attention operator. inside this operator, there is a separate dispatch layer to multiple different attention backends. Okay, quick side note on CUDAGraphs. So the problem is sometimes in LM inference you have a lot of CPU overhead. Like you get CPU overhead because the PyTorch framework has overhead. You get CPU overhead from just running Python sometimes. And so that's where CUDAGraphs is really profitable. CUDAGraphs is this technique that lets you capture. You basically play a model, and CUDAGraphs captures all of the kernel launches. And once you have captured the kernel launches, you can just replay them in the future. There are some restrictions here, like you can't capture everything. You can only capture CUDA kernel launches. You can't capture CPU operations. Hence the name CUDAGraphs. On the replay, your CUDA kernels will read from the same memory addresses as they were recorded, which means that if you have different input data, you don't want to just replay the graph with the same data. You want to rewrite that address with new data. And so vLLM does this interesting thing, because not all operations are CUDAGraph safe, especially the attention operation during prefill, for example. vLLM takes this full graph that it has acquired from Dynamo, and then splits it into CUDAGraph safe graphs and CUDAGraph unsafe regions. And so the CUDAGraph safe graphs can have CUDAGraphs applied to them. Later on, the CUDAGraph unsafe regions, they just run eagerly without CUDAGraphs. Okay, so now that we have a bunch of split graphs, the next thing we do is we call inductor to compile the graphs. So inductor will just take the graph. Maybe the graph has I don't know, the RMS norm or the rope operation in it, and it will just generate an artifact that has fused kernels for them. In addition to calling inductor, vLLM applies custom inductor passes. For example, some of the passes look will fuse silo and quantize. Some of them will fuse all reduce and RMS norm operations into one big fused kernel. And so instead of handwriting all of these custom optimizations, you could think about going into each of the 100 models and just, I don't know, fusing them together by hand. vLLM does this as a custom inductor pass. And these custom inductor passes unlock LLM-specific optimizations over the entire range of models. It's you write it once, reuse it everywhere. Finally, at the end, we've got some compiled artifacts. vLLM's custom Dynamo backend just stitches these together and applies the CUDA wrappers. So that's the whirlwind tour of vLLM compilation. I want to go through 3 more examples of how the vLLM custom compiler really controls the compilation. Okay, the first one is recompilations. Recompilations are kind of annoying sometimes. You don't want recompilations during serving. They will make your latency pretty bad. And so vLLM really controls the compilation process. In the first part, it captures a graph, one single graph that can represent all the semantics they want, prefill, decode, etc. But also vLLM uses custom Dynamo hooks to just straight up drop all the Dynamo guards that are responsible for recompilation so that it will literally never recompile. Compilation times. So vLLM also saves compiled artifacts to disk. This is leveraging Torch.compile's compiler cache. So right now, so on a cold start, you're launching a machine. It will start up the model. It will do everything in this diagram. Right now, what is cacheable is just the backend compilation part. Every time you start up a machine, even if you have run vLLM on this machine before, it still needs to do a front-end trace. It still needs to split your graphs. But at least the backend compilation is cached. The backend compilation is the largest part of the compilation time. For Llama 3.1 70B, it's around 90 seconds compilation. Backend compilation is 60 seconds. In the future, PyTorch is working on a new feature called AOT precompile that will let you cache even the front-end compilation pieces. Roughly how that works is that given a model and some inputs, this new AOT precompile API just gives you a single artifact. And you can run this artifact on some inputs. You can save this artifact to disk. You can load it from disk. And this completely like sidesteps anything, any compilation you need to do. So it'll be able to give us near zero warm start times. Okay, multigraph compilation. So vLLM like captures a graph with dynamic shape and then passes that to Inductor. It turns out that this is pretty good, like in terms of performance, but we can also eke out a bit more performance on that we have measured smaller batch sizes if we actually specialize on a batch size and turn on auto-tuning. Auto-tuning is this thing where Torch.compile can generate multiple variants of a kernel and find the best kernel for you. And so like in like this step, like instead of taking one dynamic shape graph and compiling it, takes a graph, specializes it on multiple batch sizes that are provided by the user, and then compiles code for them. And then dispatches between them in the backend. Okay, I want to touch on one last thing. Since post-training RL is becoming more important and numerics are becoming more important, in Torch.compile, we're planning on offering soon a new run-to-run deterministic mode, and also a new mode for Torch.compile to generate efficient batch invariant kernels. So no need to, eventually there will be no need to write these by hand, like Torch.compile will just produce these. Batch invariance is pretty important for vLLM in the sense that like vLLM can choose the battery data together differently, and you probably want like the same result out, otherwise you get some weird behavior. Okay, we're at the end of this talk. I want to just like say some last parting thoughts. In this talk, we showed how Torch.compile works, a variety of use cases, vLLM and HuggingFace diffusers. Torch.compile helps improve your performance and productivity via faster kernels, lower CPU overheads, and better developer velocity. And PyTorch compiler team, like as a part of the PyTorch compiler team, I think like we've been making an effort to really talk to developers in the community, see how we can integrate with their libraries, and just make them faster and more productive. So thank you. Some acknowledgements. The HuggingFace diffusers part of this talk was based on work by Sayak, Animesh, and Benjamin. It was originally a blog post. Ditto for the vLLM case study. It was originally a blog post from Kai Chao, Luca, me, and more folks over there. And last, thank you to PyTorch compiler team for the awesome work. And that's all for me. Thanks, everyone.